Welcome to part 3 of plate tectonics. In part 1 we took a look at the continental drift theory, and in part 2 we took a look at the layers of the earth, and in part 3 we're actually going to start to bridge that gap between the continental drift theory and Wagner's theory in the continental drifting, and we're going to eventually get into plate tectonics. And what we're going to now look at today is that final approach. How do we evolve from the continental drift theory to the plate tectonics theory? Okay. One of the first things I want to do is I want to get a pointer, so I'm just going to click on this. That way I can make some drawings as we go through this video. Now we're going to start by talking about the outer part of the Earth. If you remember, the outer part of the Earth consists of a relatively thin, rigid piece called plates. And in the last section, we didn't actually call them plates. I might have referred to them as plates, but I called it the lithosphere. Remember, the lithosphere is all of the crust in the very, very top part of the mantle. And this word lithosphere is used quite a bit. In fact, sometimes the word lithosphere right here is actually used with the word plates, and scientists refer to the plates as being the lithospheric plates. And these plates are continually moving very, very slowly. Now, one piece of evidence that helped bridge the gap between the continental drift theory and allowed scientists to finally, once and for all, figure out that plate tectonics is for real, is radiometric dating of rocks. And radiometric dating of rocks was perfected during World War II. And what they found out was that the rocks in the middle of the ocean, so if this, let's say this is the middle of the ocean, and we have here, let's do this. Here's North America, with Florida right here. So if I drew North America, sorry, it's not the best of drawers. And, here we have Great Britain, we have France right here. And right here is the middle of the Atlantic Ocean. What they found out that the rock in the middle of the ocean was young. And as they moved through, it got older and older and older. But what was amazing was the rock was approximately, the oldest rock was 200 million years old. So, million years old. And what was so interesting about that is when you go on land, they were finding rock that geologists, in other words, they theorized was much, much older than that. They were talking about some rock being over 1 billion years old. So why the age difference? Why was the rock on the ocean floor so much younger than the rocks in or on the continents? Another piece of evidence that really came out, that really cemented in, and this was one of those pieces that a lot of geologists, once they looked at it, they made up their minds that yes, this idea that plate tectonics is for real. So during World War II, magnometers were developed, and these were developed to search for the German submarines. And scientists used these same magnometers to discover alternating bands of rocks that were recorded. And what they found was that there was normal polarity, or at least normal for us now, that pointed towards magnetic north, but they also found some bands of reverse polarity. And they were arranged systematically along the mid-ocean ridges. So for example, when you see here, when the ships were searching for the submarines, they would also get this data. And one of the guys who found some of this data was a guy by the name of Harry Hess. He was in the Naval Reserves, but he was also a professor of geology at Princeton University. And he actually got in trouble for running these magnometers pretty much nonstop because he wanted to get this data for, for geology purposes. And here's another diagram. And what they figured out was happening was where you have this mid-ocean ridge right here, that when this magma comes up and it cools, there are certain minerals that are magnetic. And when they cool and when the magma solidifies and becomes solid, there are certain minerals in them that actually are like little mini compasses. They'll actually align themselves to magnetic north. But what they found was that there's also alternating bands, and you can see some of these bands, these white bands in here, that would point to magnetic south. Then it would be north and south. And you can see where my red pen is right here, that it would actually alternate. So this seems to match up with this one over here. This seems to match up with this here. And what geologists finally figured out, is mainly, Vine and Matthews, and there was other geologists that worked with this data as well. But what they reasoned was that this basaltic magma that rises from the ocean floor, it was actually recording the magnetic field. and the polarity. And what they figured out was that this field actually reverses itself. And approximately every 500,000 years or so, they're finding that instead of having magnetic north, we'd have magnetic south. In other words, all of our compasses, instead of pointing north, would be pointing to the south. And recently, if you read the papers, every once in a while there's an article about it where geologists are theorizing that we're due for another flip soon. And what I mean by soon, not in the next few days or few years, but over the next few hundred years, maybe 1,000 years or so, they're predicting that there will be another flip. And one of the reasons for that is they're finding some abnormal things happening with the magnetic field, and this might be an indicator that it's going to flip. So it'll be interesting. That's the first time, in recent history that we would have been through this. So here you can see these alternating bands, and it's kind of nice right here in drawing. So, here's your Mid-Atlantic Ridge, and it comes this way, and you can see how the bands line up. So, with the idea that the rock was oldest in the middle, or youngest in the middle, and it's getting older as you move out, you've got this magnetic polarity. And when they say normal magnetic polarity, well, it's normal for us right now because we're used to it being to the north. But at one point in time, reverse would have been normal as well. So you've got some of these rocks pointing to the north, some of them pointing to the south, some of them, when I say pointing, the minerals within them are aligned to magnetic north, magnetic south, and alternating. Now, another interesting thing with all this information that was found on the bottom of the ocean floor, remember at one time, the ocean floor, most scientists thought the ocean floor was just flat. They didn't know there was huge mountain systems underneath it. And it wasn't until they were able to, have things like sonar, which is basically like radar, but looking underneath, using sound to figure out the elevations of the seafloor. What they found was that there was a huge underwater system, or underwater mountain system, and they call this the Mid-Atlantic Ridge. And this ridge was running right down the middle of the Atlantic Ocean, which is why they call it the Mid-Atlantic Ridge. And this helped line everything up. If we backtrack, this ridge would have been right here. So everything seemed to point towards this ridge, and something was happening here. And again, we mentioned this earlier with radiometric dating. They found that the age of the rocks increased moving away from the ridges towards the continents. So you can see that happening right here in the diagram, where you can kind of see with my red pen where the rock would be created here. And what was happening is that as these plates are moving in this direction, I'm not going to draw on it because it's an animation, and so I don't think the animation will keep going if I draw on it. But you can see the rocks getting older and older and older as you move away. And the seafloor, again, the scientists theorize, is moving from the rift as new magma is added. So it's moving apart, but you're not going to get a huge, void in there with nothing. New magma is coming up, and it's creating new land. And what scientists found was that this mid-ocean ridge was not just right here in the middle of the Atlantic Ocean, but they found ridge systems in the Pacific Ocean, they found them in the Indian Ocean, they found them all over the world. So this was a phenomenon that was really new. So this, along with the paleomagnetism, really helped most geologists come to the realization that yes, Wagner was right. The plates weren't always in the spot that they are right now. So here's Harry Hess. Remember, he's the gentleman, the geologist, who was in the Naval Reserves. Him, along with a guy by the name of Robert Dietz, they developed the idea of seafloor spreading. And this seafloor spreading theory, this idea, was the kind of the bridge between the continental drift theory and the plate tectonics theory. And it was kind of interesting. This was one of the research ships, and this was the Glomar Challenger. And what it would actually do is it just go back and forth on the ocean floor, or not on the ocean floor, but over the ocean floor, back and forth in the ocean, and they would just drill samples, and they would bring up the samples from the rocks from the bottom of the ocean, and that's how they could do the dating of the rocks. Now, the Glomar Explorer, if I backtrack, it looks a lot like this book. This is an interesting history. They actually use this because it looks just like the Glomar Challenger. The Glomar Explorer was actually a spy ship, and it was used. If you ever heard of Howard Hughes, he was kind of like the I don't want to say he was the bigwig of his time. He was like a flamboyant actor. He had a lot of money. He created the Spruce Goose, one of those largest planes. He spent a lot of money on that. Only flew once and only flew a little ways. But it was actually used as a spy ship. This ship was actually supposed to be going back and forth in the Pacific Ocean looking for mineral deposits. But what they actually did was they actually used this ship to um, bring up a Soviet sub. And in 1974, a Soviet sub had sunk not too far from Hawaii, far enough away that it wasn't right by Hawaii. But the United States had listening stations, so they could, detect submarines coming, and they actually detected or heard this Soviet sub break up. And it was obvious after a while that the Soviets didn't know where it broke up. So they used this ship, they built this ship, and what's interesting thing is the bottom of this ship actually opens up. And I've heard various accounts whether or not they actually got this ship or not. Some people are saying yes, they brought up the sub and they wanted the technology and any code books that they had, things like that. Other people are saying no, they never got it. And it's one of those things. The United States, they're not going to actually admit if they got anything, because then at the time the Soviets probably would have been pretty mad at them for taking that data and that information and go off the sub. So I thought this is just one of those interesting things. You don't often have a spy ring and geology tied hand in hand, but here you do. Now let's get back to the evidence. New evidence was later incorporated into the theory of plate tectonics. And all this evidence basically said that the continental drift theory was correct. The one big thing was that it wasn't the continents that were plying through the ocean. It was actually the plates that move. And these are the 6 major plates: the Eurasian plate, the Indian plate, the North American plate, the Pacific plate, South American plate, and the African plate. These are the 6 major plates. Are there some other large plates like the Antarctic plate? Yeah, but these are the ones where most of the people on, these are the ones that you hear about most often when it comes to earthquakes and volcanoes, things like that. So I thought these would be, good 6 to know for the test and to know a little bit more about. Are there other plates? Yeah, there's lots of other plates. When you look at this diagram here, you can see that there's lots of different plates, and the Earth is broken into these plates. So again, we talked about the North American plate. This is where we live. We talked about the Eurasian plate. We talked African plate. These are the 6 main plates. This one right here, it's got different names. Sometimes you hear it be called the Australian plate. Sometimes it's the Indian Australian plate. Some maps you'll see actually have it divided right about here, and they have the Indian plate down here and the Australian plate right here. And then the other big one, probably the biggest plate, is the Pacific plate. And if you have to learn these for the test, it's pretty easy to figure out where they are. The North American plate is over North America. The South American plate is over South America. So when you look at where they are, this is Europe and Asia put together. It's one of those things I never understood why they get 2 continents out of it, why they divide it up in Europe and Asia when it's all connected. But it is. And are there other plates? Yeah, there's the Nazca plate. We'll talk about the Juan de Fuca plate a little bit. You got the Cocos, the Caribbean, the Philippine plate. So you hear about these plates from time to time, but it's the main plates that we're most interested in. So here you see some of those other plates happening. And the big difference between Wagner and his continental drift theory and this theory is that says it's not the continents that move. Wagner said it was the continents that move through the oceans. But no, what scientists have figured out is the plates. And if you notice, the North American plate, some parts of California are actually on the Pacific plate. But it's all of the land, plus, look, it goes out to the middle of the Atlantic Ocean. So it's not just the continents. It's the continents and the ocean. Because remember, the lithosphere is all of the crust, both oceanic and continental, as well as the very, very top part of the mantle. So what this does is makes up a large plate. So this plate covers the continents as well as parts of the ocean. Now, one of the main plates, the Pacific plate, is mainly the Pacific Ocean. But a lot of the plates, you can see the Arabian plate is half, part of the Indian Ocean, a lot of the Atlantic Ocean. So most of the plates consist of land and ocean. So when we start to take a look at where these plates are moving, you can see that some of the plates are actually moving against each other. And we'll talk more about that in the next section and what happens from that. So let's look at some plate tectonic facts. First of all, each plate is about 100 kilometers thick. So remember, the crust is only about 5 to 35. So remember, if this is going to be 100, that's because you got all the crust in the very top part of the mantle. You might say, so again, why does it range from 5 to 35? Well, on the highest mountains over the continents, it's probably going to be your 35 kilometers. When you get to the bottom of the ocean floor, this is where you're going to get your smaller distances. They move anywhere from 1 to 20 centimeters a year. Now, typically, it's going to be a lot less. Most of them don't move 20 centimeters a year, but every once in a while, through time, through research, scientists have figured out some of the plates have moved faster for some various reason. Usually they move a few centimeters a year, but they can move faster, and they have moved faster in the past, and they may so do that again in the future. And this helps to explain large-scale geological changes. Before plate tectonics, scientists, geologists, they really couldn't figure out, they didn't know why certain geological features were created. We live here in Baraboo. Why were the bluffs created? How were they created? There's lots of ideas out there, but until plate tectonics, scientists, geologists, they really couldn't put it all together and say, oh, now we understand. Because the plates are moving, this is why this happened. This is why, you got pieces of the Appalachian Mountains aligning with mountains in Europe. So now things start to make more sense for geologists. And this does end day 3 of the notes, so we'll pick it up again with day 4. As always, if you have any questions about this, if you want to talk about it some more, if you didn't understand some parts, just talk to me in class. I look forward to the discussions. Thank you, and goodbye.